Okay, so let's say that we have space-time x and t and a frame of reference that's moving at some speed v star, and therefore x bar, t bar is measured there. And there is an object that is measured in x bar, t bar to be moving at speed v bar. So x bar over t bar is equal to v bar. So v bar is the speed of the object from the perspective of x bar, t bar. Let's ask what we find when we try to do x over t. In other words, the speed from the perspective of the xt observer. So how do we do this? Well, we know that x bar is given by 1 over 1 minus v star squared, square root, times x minus v star t, and t bar, right, the Lorentz transformations, is 1 over 1 minus v star squared, same factor, times t minus v star x. And we want to construct, we know what this quantity is, so this divided by this is that. So we have v bar is equal to this divided by this, and that gives us x minus v star t over t minus v star x. And we need to turn this into an object that has this quantity, right, x over t. And so we see that we can get two v's in here, and everything else will be known, and we'll be able to solve for that v. So this looks like, let's do 1 over t here, and therefore 1 over t here, and that is x over t, which is what we need, minus v star over 1 minus v star x over t. So that is v minus v star over 1 minus v star v. So we have two v's, one equation, one unknown. And the equation is, let's write it all out, v bar is equal to v minus v star over 1 minus v star v. And so we want to isolate the v. And of course, the first thing we can do is to multiply both sides by the denominator here. So we get v bar minus v bar v star v equals v minus v star. Let's bring this term to that side and this term to that side. Of course, that gives us v bar plus v star is equal to v plus v bar v star v. And of course, this gives us v bar plus v star is equal to, pull out the v, which is what we're trying to do, isolate the v, 1 plus v bar v star times v. Now all we have to do is divide both sides by that. So we can get v is equal to v bar plus v star over 1 plus v bar v star. So that is the speed of the object as measured in xt. So let's think about what happens if, if the speed of this object approaches the speed of light. So let's say that it is light, right? We know that if this is a particle of light, then in x bar t bar, the speed will be the speed of light, which is 1, because we don't have this factor of c here, right? C is equal to 1, so v bar equals 1 means it's the speed of light. This needs to reduce to the speed of light. That's the whole point of the special relativity, right? The Lorentz transformations. So let's look at that and make sure that that's the case. So v equals v bar, which is 1, plus v star, right? That's the speed, that's the relative speed between the two frames. That can be anything, over 1 plus v bar is 1, so that this is 1 plus v star, and of course that's equal to 1. So that makes sense. Let's see what this looks like. So this is one special case. Let's do another special case here. If, say, the speed of the object as measured in the x bar t bar frame is very slow, it's barely moving, then we know that this has to give us something that we're familiar with. In other words, the special relativistic effects disappear, and we should just get that that we sum the velocities. So let's see that. So v is equal to v bar is much less than 1. So here's v bar, and so here we have whatever the small value is plus the relative velocity divided by 1 plus v bar is very small. This is v star. This doesn't have to be very small, but this is, we're really divided by a factor of c squared in here. So this term, well, we could also just look at it from this perspective, right? So v stars is less than 1, and this is much less than 1, and so this is basically just 1. And so in fact, the velocities just add in the non-relativistic limit.